NewSQL is a class of modern relational databases that seeks to provide the same scalable performance of NoSQL systems for OLTP while still maintaining the ACID guarantees of a traditional database system. VoltDB is one such NewSQL system. It's designed in part by Turing Award winner Michael Stonebraker. Today's guest is John Hugg, an engineer at VoltDB. We discuss the internals of VoltDB, including concepts like tunable consistency, database replication, and the advantages of a deterministic logical log. If you liked the earlier episode that I did about VoltDB, you will enjoy this episode. But before we get to the interview, we have a message from a sponsor who keeps Software Engineering Daily alive. Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. John Hugg works on VoltDB, an in-memory database with streaming analytics and transactions. John, welcome to Software Engineering Daily.
Thanks for having me.
Let's start by talking about how VoltDB works. What is unique about VoltDB?
VoltDB, one of the things that makes it a little bit unique is that it came out of an academic research project. So a lot of very, very bright academics, including Dr. Michael Stonebraker, and Dr. Andy Pavlo, Dr. Daniel Abadi, Stan Zadanek at Brown, lots of these people got together and kind of came up with the research that sort of rethought how operational databases should work. And that research, after writing a bunch of papers, building a bunch of proof of concepts, showing that this is a credible idea, is the technology that has been commercialized in VoltDB. So that's something that's a little bit of a different pedigree. It's not just a bunch of people who came out of the industry and said, we can take the same ideas and do them a little better. It's a real fundamental rethinking. And some of the core ideas there is, what if we looked at assumptions from the 21st century or even more recent than that? What if we looked at assumptions from 2010 to 2016 and we say, well, what's different than when a lot of these systems were built, whether that's 10, 20, 30 years ago? And so taking those assumptions, kind of things like, we've got a lot more CPU cores. We've got typically people want to run their services on a bunch of virtualized commodity hardware, whether that's in the cloud or whether that's in their back room. What they don't want is big iron. They don't want mainframes. People want to run on machines that have lots of memory. The difference between CPU and memory and disk is all very different than it was in the 80s and 90s when systems like Oracle were designed. So that kind of led to, well, how would the architecture look different if we were building a system today? The other big change is that people are building more specialized systems. So whereas when you say MySQL was designed to be a general purpose relational database that can do queries, that can do updates, that can do basically whether it's operational, analytical, anything you need a database for. MySQL is sort of designed to be all things to all people. And that's not that different from SQL Server or DB2 or Oracle. And so what happened is we started to see, 10 years ago or so, a lot more push towards specialized analytical systems. Systems like Teradata and Netezza, ultimately things like Vertica, and now in the cloud we've got things like Redshift. And Hadoop systems that are very good at doing analytics, whether that's Impala, Hive, or a number of other systems. And so because those systems specialized on analytics, they were able to do better at analytics than the general purpose systems. And so VoltDB came at this problem and says, well, what if we specialize on the fast data part of big data? Right? What if we specialize on the operational workloads, the things where the uptime is important, where the data security is important, where the data protection in terms of, is the data going to go away if something crashes, where that's very important, where the update rates are very, very different than the read rates are for an analytical workload. So Volt, kind of summarizing, came at this with modern hardware, modern software engineering, modern deployment, and came at it as an operational focus.
So we've got a set of first principles that are being questioned, and then we have on the other side a broad set of use cases, a general set of analytics work use cases that. And with these intersections of things that these researchers were thinking about, that led to VoltDB. So zooming out a bit and thinking about like the customer use cases, could you give some examples for where VoltDB would be a good fit? I mean, I know that's fast forwarding from the research perspective, but just to put things in context.
So Volt is, the funny thing here is that we're in a lot of verticals, right? We're in telecommunications, we're in online gaming, we're in ad tech, we're in finance, we're in the Internet of Things and smart meters, we're in micro personalization, lots of different verticals. But a lot of these apps have a lot of overlap in terms of what they look like fundamentally. And I would say some of the key overlap for Volt is we see apps that have very, very large volumes of sort of horizontal scalable writes. So often this is some kind of an event stream or a set of actions that's being sent to VoltDB for processing. Now, in different verticals, that could be a different thing. It could be we want to show an ad to a user in ad tech. For online gaming, it could be someone just beat level 5 in 30 seconds. Should we make level 6 easier or harder? In telecommunications, it could be this user is in this place and would like to make a call to this other number. Should we let that call go through? And so there are many different kinds of use cases, and they seem really different. But they're all sort of these very wide ingestion problems where a very wide set of actions are arriving at Volt, and Volt often needs to combine some kind of analysis with a decision. And that means that Volt wants to say, should I let the call go through? How hard should I make the next level? What ad should we show the user? So it's not just an analytics problem where the flood of information is coming in and we're saying, oh, well, here's how many of these happen. Here's some interesting trends. What it is an actual, on a per event, we're making decisions that affect things.
Okay, so as you're characterizing this, you have to you're making decisions. So this is like kind of not the traditional way that we think about databases, or at least the way that we're taught in school. Database is just you can do a write and you could do a read, and that's about it. And once you start bundling the ability to do stuff that was previously decisions on the part of the application, what are the challenges that emerge from a design perspective? I mean, if you're putting application logic, or what was previously application logic, into a database, what are the design challenges there?
Well, it's still application logic. And I will say that there's sort of, for the longest time, if you look at sort of traditional databases, you've got your application logic in one side, maybe that's in one language, and you've got your set of queries, your SQL, or if you're not using a SQL database, some other set of data access operations, and these are separate. Sort of the line between them is sort of in one place. And when you get into a lot of the really high volume event processing, whether you're talking about VoltDB, whether you're talking about stream processing like Storm, whether you're talking about batch processing like Spark and Hadoop, what you're seeing is that there's a lot of value in moving logic to the data rather than moving data to the logic. And the issue here is the data is a lot bigger than the logic. Simply a bunch of ifs and thens does not take up a lot of space. However, we're dealing with gigabytes, terabytes, petabytes of data. So taking that logic and moving it around to wherever the data is the smart thing to do. And what we're effectively doing is we're moving the line between how much is in the database process and how much is sort of in the client app server process, a little bit towards more towards parity, where there's some of your code in both, and a little bit less towards very heavy app server code. And what that allows the database to do, and in this case, Volt, we call it a database, but whether it's a stream processing system, whether it's a distributed processing system like Spark, it's all the same idea. What it allows it to do is to be very smart about how it applies that logic to your data. It may be that it takes that logic and breaks it apart and applies it in multiple places, so that if your data is distributed across 100 servers, I can apply some of the logic at the 100 servers, collect that data or move that data around, and apply the rest of the logic in a way that's very efficient in terms of network data movement. In the old days, the biggest way that sort of databases would optimize is to reduce the number of disk reads. And one of the big changes nowadays is that one of the ways we can optimize is to reduce the number of network reads. Moving data around between two machines is one of the most expensive things we do. So anything we can do in terms of executing your query or in terms of executing a whole bunch of stored logic to move less data means our system is going to perform better and have more responsiveness.
Okay, so I'd love to start getting into the weeds here. Traditional databases suffer from locking individual records when there are multiple queries being run in parallel. Could you describe in detail how VoltDB avoids this problematic locking from multiple queries?
Yeah, so Volt makes different trade-offs, and I say trade-offs because I'm an engineer and I'm not in sales or something who would say that that everything is free. But I think it makes trade-offs that make a lot of sense in the context of the problems we're trying to solve. So what Volt does is instead of using it like a shared memory model where you have a whole pool of operating system threads or whether they're fibers or green threads, it doesn't really matter, but a whole pool of sort of actors all hammering at the same set of shared data in memory, where you've got to have some kind of shared locks to manage concurrency so people aren't accessing the same data. Even if you're using lockless data structures, these things have a tremendous amount of overhead in terms of the complexity of the code, in terms of the amount of code that needs to be executed, in terms of some of the consistency you can get out of those systems. What Volt does is Volt says, you know what? If I've got 12 cores, I'm going to partition my data 12 ways. I'm going to split up my data. This isn't like an Oracle partition. It's sort of a shard kind of view of databases. I'm going to split up my data into 12 chunks across my 12 cores. And then what I'm going to do is I'm going to give a single thread of execution to each of those 12 chunks on each of my 12 cores. And I'm going to schedule work to each of those 12 pipelines. Now, because today everybody wants to run clusters of databases, we already have to split up your data between servers. Any good modern system for doing these kinds of operational workloads is going to support 10 nodes, 20 nodes, however many you've got. So if we have to divide our data anyway, it's a logical extension of that to divide it even further so that we have many individual shards on one machine. Once we can sort of route your work to the right shard on a different machine, we can also route your work to the right shard on a core. Now, this has, in terms of throughput, there are tremendous advantages to this situation. It's the absolute most efficient way to get work done on your machine. In terms of concurrency, it is the absolute most efficient way to manage high contention rows in your database. If I've got one row, ultimately the fastest I can have is a single, very simple piece of code running as fast as I can on one core. If I add two cores to modify one row, I can't actually make that really any faster. So if I have many high contention rows in Volt, Volt is going to be faster than anything else out there at managing that contention. The downside to sort of this, and there are actually some additional upsides, but just the flip side of this is that if we have sort of long-running work on VoltDB, so work that needs to scan all of the rows, then things line up behind that work. It doesn't mean that the overall throughput changes. We still have to do all that work somewhere, but it means that if I do an operation that takes 1 second, it actually locks the entire either the entire shard or the entire database for that 1 second while I'm doing that operation. So Volt really favors operations that are very, very fast, and we do a lot of things architecturally to make sure that operations are very, very fast. And I can go into some of that. I can also go into some of the other advantages. I'm not sure.
Well, let's. I wanted to touch on the concept of database replication. That's what I was thinking would be interesting, because the way that Volt does database replication is quite interesting. And it's not closely related, but we can evolve in the direction of the conversation we were just having.
Yeah.
But so in terms of database replication, so this is like a canonical problem in distributed systems, and we've done several shows that have touched on this topic. So just from a more basic perspective, what are the ways that developers can typically set up replication on their database?
Sure. So from a user perspective, how the user sets this up, Volt has a concept of clusters, and a cluster is a set of machines connected by a reasonably low latency connection. So that means within a data center, typically within one Amazon availability region, within one floor of your building, but not distributed around the world. And then within that concept, within one cluster, you can connect multiple clusters, and that's how Volt achieves high availability across data centers. Within a cluster, what you can do is specify a redundancy level. So you say, I've got these 10 machines, they're running Volt. What I would like is 3 copies of every piece of data. And that's just a declarative configuration to Volt that says, make 3 copies of my data. You don't need to worry about which of the machines have copies and which of the machines are the primary. In fact, because as I said before, we split up things into littler chunks than that, the machine is going to have some sort of primary copies and some secondary copies depending on the core you're looking at. And what we do is basically we manage where data lives. We have configuration to ensure that, for example, you don't put both of your copies on the same host machine for 2 virtualized instances and things like that. If you've got multiple racks of servers, you can have it so that we make sure that that copies of your data are on different racks if possible. But you specify a redundancy level within the cluster. And then you can specify, if you have multiple clusters, how you're going to replicate data between those clusters, whether it's an active-passive replication or whether it's an active-active replication between clusters. Does that make sense from a configuration standpoint, what the users see?
Certainly. And the something that VoltDB does that's interesting, kind of extension of this conversation, is VoltDB creates a logical log so that different databases in the cluster can do the same operations in the same order to 2 copies of the same state.
Yes.
Can you describe the structure of this logical log?
So Volt within a cluster, I mean, I can talk about multi-cluster stuff later. Within a cluster, Volt basically uses replication. We basically take these little shards of data that are in each core, and we buddy them up. So if you say I want 3 copies of data, you're going to have 1 core on one machine, 1 core on another machine, and another core on a third machine that all have the same data. And rather than have a primary that does some work and then takes a change set and sends it to the replicas, which is the way most systems work, Volt is very different. Volt actually executes the same operation against all 3 copies of the data at the same time, even if that operation includes lots of stored procedure logic and many SQL queries all bundled up. What we do is we leverage determinism to ensure that we have the same data at different places. So I said before, we sort of have this pipeline of work, and it's single-threaded at each core. So we do sort of one thing after another to this shard of data. And what we actually, by leveraging determinism, if we say all of these operations that we're doing one thing after another, and this is sort of a logical log, right? There's a log of, I'd like to run procedure A with these parameters, procedure B with these parameters, and procedure C with these parameters. That list of the procedures, their parameters, some SQL statements and their parameters, that list with that specific order and those specific parameters is a logical log. We can write that log to disk, or we can replicate that log across the network by assuming we have the same state in 2 or 3 places. If we apply the same set of deterministic operations in the same order to the same state, we end up with the same new state. And so Volt does, instead of doing one thing at one partition, then copying to the next, then copying to the next, we do all 3 at the same time. This has tremendous latency advantages for us. So Volt runs synchronous serializable isolation, full ACID serializable isolation with synchronous consistency, no matter how many copies of the data you ask for. And we can still do this with very, very low latency. Typically, a millisecond or two, because of the way we're not chaining things, and it's synchronous. It's not we write to one and confirm to the client success. We write to all of them and confirm to the client success. And that's actually the only way Volt operates. We don't have a lower consistency model within a cluster because there aren't advantages given the Volt architecture to having a lower consistency model within a cluster.
I love being a software engineer because of how easy it is to build side projects. And I've built countless side projects. I've built a social gambling application, a dating website backend that had 0 users, a stock trading music rhythm application for Android. And I think every developer should have side projects. So when I have a web app that I want to deploy and share, I want to show my friends my most recent project that nobody will care about, I use DigitalOcean to quickly spin up a server and host my projects. And who knows, if one day one of my apps takes off and goes viral and people actually do care, I can easily scale using DigitalOcean's flexible pricing plan. Companies like TaskRabbit that have grown rapidly have used DigitalOcean for this very reason. But until this happens, I will happily stick with the $5 a month plan. Sign up with promo code SEDaily to get a free $10 credit as a listener of our show and start building your apps. We would love to see what listeners build, so send us an email showing us your project. I've also interviewed Moisey Uretsky, who is the co-founder of DigitalOcean, and he mentioned that the ease of use and the flexibility is why they built the service in the first place. That DigitalOcean interview is one of my favorite episodes. Moisey talks about bleeding in a data center. He says, you don't know how hard it is to do a cloud hosting service until you've bled in a data center. It's really interesting. So speaking of which, let's get on with this episode of Software Engineering Daily. So I want to touch more on this topic of determinism, because this is something that it's like a key word that I hear around VoltDB, and I haven't heard in a lot of other conversations around databases. Obviously, I know the word determinism, but in the context of databases, what does determinism mean?
Sure. So the one of the key differences is sort of the difference between a logical operation and sort of the binary changes that come from that. And one of the reasons you don't hear about it a lot is that a lot of people use databases for reads, analytical reads. I run a query, I get some results. That doesn't necessarily need to be deterministic for most cases. Nobody cares that much if that's deterministic. People use databases for a lot of sort of key value update workloads. And especially the NoSQL systems, they're predominantly key value update workloads. If I have a key value workload, the difference between saying the logical operation is I want to update this key to this value, really the binary operation is the same thing. The new value of the key is the change log. Where it gets interesting is in Volt, where I'm moving the logic to the server, and my logic can be quite significant. I can have a logic. So say I'm a customer that runs a cell phone network. And my stored procedure is this phone number wants to make a call to this phone number from this place and this time. Should I let it through or not? This actually might run 10, 15 SQL statements, or maybe 100 SQL statements. It's going to look up, well, what are the last few numbers this person has called? What do we know about this person? Are they on any blacklists? What do we know about the number they're calling? These are all sort of read SQL statements. And then we take those SQL statements and we write. We write a log of, did we let the call go through? Here's the call. Here's the account we billed it to. Here's how the billing information is going to change. Here's a record of the start of the call. When the call hangs up, we might write a completed record of that call to a downstream system for analysis. So there's a lot of logic in this stored procedure. And when we say the stored procedure is deterministic, what that means is that if the state of VoltDB is the same and the parameters to that stored procedure are the same, then you will always end up with the same action. You'll always get the same writes to the database, and you'll always get the same decision out on the other end. So that means if I say, show me some recent calls by the user, it's never going to be a different set of recent calls. It's never going to be, well, there was a race condition, so instead of these 5 calls, I got one that didn't make it the last time I ran this procedure. That kind of determinism. If it's never going to be because they were technically the 5th call, there was a tie. There was 2 calls at the same time or something, and one time I queried, it returned one of them as the 5th call, and the other one it returned the other. That doesn't work.
So do you think of determinism as like multi-operation atomicity?
So yeah, it's partly that. Partly it's the idea that if I wrote a snapshot of the state to a log, and I wrote the stored procedure with the parameters to a log, I could wait a week, load that state in, run that stored procedure, and I'd get exactly the same answers and exactly the same changes to state.
Okay. So the difference between my definition of multi-operation atomicity is like you could change the time of the system, for example,
right,
and that would have no effect on the determinism of the operation.
Right. So Volt asks that if you want to ask what time it is, that you use our APIs for that. If you want to get a random number, you use our random numbers that have been carefully seeded, so they'll always have the same seeds every time you run this transaction.
Right.
Because we use this for replication within a cluster. We also use this mechanism for fault tolerance on disk and for repairing failed nodes into a cluster. So, for example, if a node fails and we replace it with an empty node, the first thing we're going to do is copy the state over to that node. But while that state is copying, we're going to keep that logical log around, and then we're going to replay that logical log onto the new node until it is caught up with the other nodes. So that may happen minutes, hours later, depending on lots of factors. And so we need to make sure that even though that happens at a later time, even though the random number generator may be different, that is a deterministic operation, it will always give us the same value.
This is a good opportunity to talk about some of the points that you touched on in a conference talk that you gave called Non-Determinism for Performance and Testing in Distributed Systems. I'm sorry, what was it called? All in with non-determinism for performance and testing in distributed systems.
I think it was all in with determinism, but yeah.
All in with determinism. Okay, so
yes.
Right, third time's a charm. I will put in the show notes with the correct title.
Yeah.
So you're touching on this idea of determinism and it being important, in VoltDB's case, you access the VoltDB API for these things that can change. Is this like a really big hazard for applications where you can end up with really troublesome situations if you're accessing the time and you get something wrong, or you're accessing a random number generator and it works in a way that you don't expect, or like how can this manifest into real world problems?
So if you have our stored procedures in Volt are typically written in Java. Technically, you can write them in other JVM languages, but for the most part, people write very straightforward business logic in Java. Now, there are in practice, the ways you can hit determinism are random numbers, wall clock time, and we don't prevent you in your procedure from calling Java util date, give me the wall clock time, or system current time millis, or any of those things. So that's one way. And other ways you can do it is you can call to an external system within your stored procedure. So within your stored procedure, you could make a call over a socket to another system and query that system. Since that query isn't guaranteed to give you the same value or even work hours later, then that could be a source of non-determinism. And then there are some sort of nuanced ways to run into non-determinism, such as maybe you're using a third-party library that randomizes things for security. We've run into that one once. The nice thing about VoltDB, in practice, these aren't typically big problems. Because what people typically do is they take their set of procedures and they're building sort of an application that they deploy onto VoltDB. It's almost like a data API onto VoltDB, and what they often do is they test that API in some way. And so we found that for the most part, people find anytime that they've done something that's going to be problematic, they find this very quickly in their test process. And we're very clear to say, when in all of our training and documentation, don't call system current time millis in your procedure and then feed that procedure into some write that's going to either change the result of the decision or change the state in the system. And so in practice, I think I said at the time I gave that talk, which was in September, that we haven't run into these sort of non-determinism problems in production in over a year. And we haven't run into them since. So we've run into some problems. Customers.
I thought you were going to say you jinxed it.
No. So in practice, we have not seen this become a problem in production. Users have not lost data because of this in well over a year, coming up on 2 years because of this. And this is a lot of the work we've done to make things easier to detect. I should say, if this does happen, we don't actually lose data when this happens, but we do restrict availability. So what we'll do is if you have a non-deterministic operation, that is a procedure does one set of data changes in one partition, one replica copy, makes another set of changes in a different replica copy, or a different set of changes on a restore or a rejoin into the cluster, we will detect that and we will save all of your data, and we will actually save both copies of the diverged data and say to you, well, what do you want us to do? So it is an availability issue. It's not a data safety issue.
So you enforce safety, but not necessarily liveness.
Right. So we have, but that hasn't been an issue in some time.
Sure. So, okay, talking about determinism versus non-determinism and how to implement that, like we touched on the idea of the logical log earlier. The logical log creates the source of determinism that is shared across the entire database. And in theory, this sounds great, but in practice, what are the difficulties of implementing determinism on a distributed database?
So one of the things that we have had to do is to be very careful about row order in VoltDB, so that we've actually built a SQL planner, optimizer, and execution engine that can be aware of when it might be returning things in arbitrary orders and when it's going to return things in a specific deterministic order. And we can actually pick plans that are slightly less efficient if we know that the output of a read plan might be fed into the input of a write operation. And if a read is not going to be fed into a write, then we don't care if it's going to return a different answer, right? That matters less to us. So that was something that took a lot of work. We've also built a lot of functionality into Volt to detect this without being super invasive. So one of the things that we do is we build hashes of all of the write operations and their parameters that you do within your stored procedure. And we compare those hashes when the procedure is returned from multiple replicas. And that's actually our primary mechanism of detecting when you've done something non-deterministic. The other thing we can do is we can compare our transactional snapshots. In VoltDB, when we snapshot your data to disk to save it, we do this on a continuous basis. That's done at a particular transaction ID, a logical point in time across the entire cluster. So if I have two replicas that are supposed to be identical, their snapshots are also supposed to be identical. And we can tell from checksums in those if we have any problems that way. So a lot of these things are sort of we've spent a fair amount of time on how we detect if you have problems. We spent a fair amount of time on building a system that's more robust to having those kind of problems. We've had some learning experiences. A thing that happened, I think last summer, is we ran into issues that we just should have foreseen but didn't. And this is something that came up in testing. It didn't come up in production. But floating point math is not commutative. And floating point math not being commutative led to some queries that we thought were deterministic operating on floating point operations, not actually being deterministic. And so we now have that as part of in our system today. We handle floating point math a little bit differently.
That's interesting.
We've had some issues with non-ECC systems corrupting memory and diverging that way. And the cool thing is that we can detect that. But it is often a difficult thing to tell someone why when that happens. We don't have it.
Right.
Sometimes we just look at it and we say, well, we don't have a great answer. Can you run memcheck off of a boot disk? And that often can be illuminating in those situations.
Right.
But fortunately, all the RAM in Amazon and most of these clouds and most systems people are buying is ECC memory, and that makes a big difference.
Okay. And so one of the ways you encapsulated this way of implementing determinism on VoltDB, you touched on this in your talk, is deterministic sequel. Can you define deterministic sequel?
Sure. So let's say I have a classroom, a table that stores all my students. I have 30 students. Let's say there's 14 girls and 14 boys. I'm being a little gender normative here, but it's good for a database example. Now, if I say select from the database where gender is male, limit 5, which 5 boys am I going to get? Depending on the database, depending on how it's implemented, you might get different guys. Right, so I might get different guys at different replicas, in fact, in VoltDB typically. And so what VoltDB will do is it will recognize whether or not that query is just a query that's going to be returned back to the user where the user doesn't care, or if it's part of a procedure of logic that's all read-only that's never going to modify state, then it doesn't matter. We're just going to give you any 5 guys. However, if you tell us if it's in a read-write procedure where I'm going to take 5 guys and I'm going to give them, say, 10 bonus points on their exam, because I'm sort of a chaotic neutral professor. If I do that, then I want to make sure that it's the same 5 guys in replica A and replica B. And so what Volt will do is Volt will basically sort your 14 guys on maybe their student ID number or something. And it doesn't have to usually do that sort in real time. Usually there's just an index where I can walk the index on student ID number and make sure that I get the same 5 guys. It might be a slightly less efficient way to do the work. In some cases, it could be a lot less efficient. If you don't have any indexes on the table and you've got billions of records, ensuring that you get the same 5 guys can be challenging. But if you're aware of these problems, if you've run your example in pre-production and test, then we can sort of tune a lot of these things. We often just basically can make that query, a microsecond slower, but then make sure that we're always returning the same 5 people from your class.
Okay, and so VoltDB's deterministic sequel guarantees that writes are always deterministic. Explain how a write works in VoltDB, and then we'll contrast that with how a read works.
Well, a read in VoltDB. Sorry, I started with the opposite of what you said. A read in VoltDB can go anywhere, right? If I have 3 replicas, I can send the read to any of those replicas. It actually doesn't matter where in the deterministic order it goes, as long as it goes in that deterministic order somewhere. A write is different in that a write has to go to all 3 replicas if I've got 3 of them, and writes all have to be ordered in the same order relative to each other. I can slot in reads wherever I want, but relative to other writes, I need to do things in a particular order. And when I say write in VoltDB, what I'm basically saying is I've got a transaction that that has the potential to write to the database. So even if a transaction does a bunch of reads and then has an if statement that says, if all of these things are true, store this record in the database, otherwise don't bother, that might write to the database. So we still call that a read-write transaction. It still has to be run at all three replicas. But when I say a write transaction, many of these write transactions have many SQL statements that are a mix of queries, logic between queries, and writes, or even potential writes. It doesn't mean they have to modify state. It just means that they might.
Interesting. Okay, so are there any other features of a deterministic SQL system that would be worth touching on?
So one of the things, what this allows us to get, just sort of circling back a little bit, I mentioned this a little bit before, there's a big latency advantage here for us. Because we can do the work on all three replicas at the same time. Again, I could have 4 or 2, but all the replicas at the same time, I don't have the latency penalty of doing one and then the other, or the consistency penalty of doing one, returning to the client, and hoping that it makes it to the other 2. So there's a big latency advantage, and that latency advantage doubles when we involve the disk. Because what I can do is write the logical log to the disk as soon as I've decided on the ordering of the operations. Typically, with systems that use memory and disk, I make the changes to the memory version, and then I write that version to the disk. So the client has to decide, do I want to be notified this succeeded when it writes to memory, when I've sent an asynchronous I/O request to save it to disk, or when I've f-synced the disk and confirmed that it's on the disk, then I want to return. But if I'm doing these things one after another, right, I'm doing the work in memory, then I'm asynchronously sending an I/O request, then I'm waiting for an f-sync that confirms that I/O request is actually on disk. If I do all these things one after another, it adds to my latency. And it can add a lot to latency. With VoltDB, what I can do is as soon as I've decided on the order, I can start writing that information to disk. And so in order to respond to the client that this is safe on disk and safe in memory on multiple machines, I actually can do all of these things concurrently and just wait for all of these conditions to be true to respond to the client. But since they're all done concurrently, if my disk, whether I've got an SSD or a disk controller, is capable of f-syncing once a millisecond or once every 2 milliseconds, then typically the latency to do the work and to respond to this query is going to be 1 or 2 milliseconds. And that's very different than systems that involve disks that have non-logical operations.
Right. So you've essentially defined why the deterministic logical log allows faster replication and faster persistence.
Right. So the second big advantage is it allows us to be very consistent in terms of this not just the determinism, but the architecture of doing determinism things in a replicated way, but doing a set of things in a log applied to a single core and a single piece of data attached to that core. That architecture is not just very multi-core friendly because we've got a lot of cores. It's not just very cluster friendly because horizontal partitioning is important for clusters, but it's very very fair. It's very very efficient. It lets us have basically our goal as VoltDB engineers is to keep your CPUs saturated with work. And this architecture lets us get as close to achieving that goal as possible in terms of throughput. Almost none of our customers are anywhere near saturated CPUs. But they love the fact that if their workload doubles, the impact of their performance in terms of what is the latency added to their API is almost unnoticeable. VoltDB performance and latency is very predictable as you go from 0% load to 90% load. It's very predictable whether you have one client connected to a Volt database or if you have 100,000 clients connected to a Volt database. Because everybody's just lining up. If you're generating all your load with one client or you're generating a little bit of load but with many clients, if the load is the same, then the performance typically is about the same. There's a little bit more networking work to be done with 100,000 clients, but surprisingly, Linux is very good at this, and we scale very well as you add clients. There's no way to add contention in VoltDB as you add more clients.
Okay, given that you've you're an engineer, and you said you're willing to talk about trade-offs like they're trade-offs.
Sure.
You talked about the trade-offs in your talk about enforcing determinism in a database, and the first trade-off you explored was that it's simply more work to enforce determinism. Can you describe how determinism led to additional engineering work?
Well, I think maybe we've covered this a little bit. I mean, in terms of the adding all the checks and the hashing and verifying the data is the same. In terms of the deterministic SQL planner and building sort of that kind of smarts into the product. In terms of testing, there's a lot of testing that we've built that sort of ensures that all the code that we think works actually works. Anytime you write code, it's usually twice as much work or more to actually verify that it's correct. And verifying that code is correct is very important for us because, this is code that people bet their business on.
Right.
So I think that's the first trade-off, the additional work. I did mention some others. There's a trade-off where I think I mentioned where there's an availability impact if the user gets it wrong. So that's a trade-off. In terms of the determinism, one of the things that we found that's challenging that I mentioned in that talk is that we assume that we've got identical software running on every cluster node. And one of the things that makes challenging is upgrades to VoltDB. So if I want to do a rolling upgrade where I'm running version 5.x on one node and version 6.x on another, then we worry as engineers that, well, if we've changed the code, how can we ensure that the same operation is actually going to make the same changes in both? What if we've modified an algorithm? What if we've ordered something a little differently and we get different values? And so Volt is very careful about how it manages upgrades. We have a patch live upgrade system where we can, if you've got, say, version 5.8 and you want to run version 5.81, we can do that because we've qualified that these things actually have, they're compatible determinism-wise. However, it makes things like upgrading an entire cluster from version 5.8 to, we're coming out with 6.0 in a week, to 6.0, it will be more challenging. And so our answer to that is, the historical answer has been stopping Volt and restarting Volt is not an operationally challenging thing. It does require a service window. It does require some time, but typing wise, it's the easiest thing in the world. I type Volt shutdown, I type Volt restore, and I'm back in business with a new version of Volt. We make sure that all of our disk persistence is compatible across versions. We do have a new answer starting with the 6.0 6.x line of code. Where we're able to use our multi-cluster support to basically bring up a new cluster with a new version in parallel. And we use, instead of a logical stream, we're using a binary stream to replicate to that new cluster. We can have both clusters running in parallel, and then we can shut down the older one. This is a very cloud-friendly way of doing upgrades. And so our customers who are running virtualized, who are running in the cloud, this is an acceptable solution for them. It's a difficult thing if you've got 3 servers in a back room. For those people, it's still major upgrades of Volt still require a few minutes of downtime. We may at some point get to sort of internally versioning some of the execution code so that we can support mixed versions of Volt in a live way. But that is one of the trade-offs of the system.
So you did touch on testing a little bit, but I am curious, like, as you're developing a database, I mean, what kinds of testing frameworks and unit testing and performance testing do you do, or how do you model that process in order to know that you're doing things in a way that accurately models the set of customers that will eventually be using your database?
Well, that's a really loaded question. It's a good question. I'm probably going to answer half of it and forget the rest. So definitely poke me on what I don't follow up on. The last thing you said about customers, well, one of the things we do talking to customers is that when customers run into issues, and this is not even just customers, but pre-customers, when we approach someone and they're looking at VoltDB and they say VoltDB is great, but we have issues when we're doing this. A lot of times what we'll do is we'll build a POC to verify, like, okay, well, surprisingly, this was more challenging than we thought. Very often, that code makes it into our continuous testing process. So we've got a bunch of internal continuous testing processes that are all named after either customers or groups that didn't become customers, where they had a workload that wasn't a great fit, and we built sort of an app that simulated that workload and beat on it until it worked well in Volt. We don't do that for every workload. Some workloads we decide, well, that really isn't a great fit for Volt. But when we think we should be able to do it, that becomes part of our process. And so that's one way we can incorporate a lot of the customer work in terms of that. We had another customer that is very latencies focused. A lot of our telecommunications customers, they choose Volt basically because there are not a lot of very, very robust operational databases that have very, very predictable latency parameters for the sort of complex server-side logic. Largely in the telco space, we're replacing times 10 or other, really beefy sort of older systems that have been very, very hardened. And so that's really there's a diversion, but really flattering for us because we know these people are sort of betting their operational business on Volt, and but one of the ways that we got to that point where we can do this is we work with these customers to build tests that run for long periods of time and measure latency the way they measure latency. So it's very common in distributed systems to talk about, well, no one cares about average latency. If you're monitoring average latency, then you're failing. But whether you're monitoring average or 99th percentile or 99.9th percentile, what we're basically doing is flipping that around entirely. And we're running queries where we're counting how many operations took more than 50 milliseconds. And our goal is to get that number to zero or vanishingly close to zero for runs that take days. Even when sending, significant load to VoltDB. And so that was a long process. And there's actually that talk that you're referencing from Strange Loop last year. There's a talk by Ariel Weisberg the year before at Strange Loop about sort of how we got that latency down, that long tail latency, and how we sort of and that was a mix of software tuning. It was a mix of Java tuning. What's the right garbage collection method? What's the right pattern of accessing these objects so they're garbage collector friendly? We certainly, diverging a bit, we make sure that all of our actual long-lived data, all the SQL data, all the SQL execution, that's all done in native C++ code. None of that is done in any Java code. We don't really want to ask you to run Java code with a 128 gig heap. It will not go well. This is something that the Cassandra people have figured out over the years, and they're sort of coming around to all of this data needs to be off of the heap. But we've built a very garbage collector friendly bits of code that run Java. And his talk is a little bit more detail about how we did that. But this process where we are measuring latency for days and counting the 50 milliseconds, when we ship a version, and this was, 5.1 or something, or 4.6, I'm not sure exactly. When we shipped this version that this customer accepted, and they started running, a third of the world's cellular traffic on VoltDB, what we didn't do is stop there, right? Right now, we actually had a recent issue where, lo and behold, VoltDB 5.8 has a slightly worse profile on the 50 millisecond system. And so we actually worked very hard to figure out what that was and to get that back down for 5.9 so that the user could upgrade to 5.9 from whatever 5.x version they were using. And that's something that, as we improve the software, sometimes we regress, and we have to make sure that test enables us to figure out what the regression was. Sometimes it's a lot of git bisect work, and figure out why that weird change that Git says is the problem actually impacts latency for, one transaction every billion or something. That's not a fun process, and we spend a lot of time on that. But that's one of the ways we get customers involved. Another thing I do, and I talk about this in the in that talk at Strange Loop, which is on YouTube if people are interested. I don't know if there's like show notes, we can link to it. But
yeah, absolutely.
But one of the things we do is we build pathological workloads. And these are just the opposite of that. They're not representative of what kinds of things the customer does. and we have this workload that we built that we call Transaction ID Self-Check 2, and it doesn't matter why it's called that. It was the second one, and what it does is it tries to be as intertwined and horribly transactional as possible, such that if we ever were not 100% delivering on our ACID guarantees, on our cap consistency guarantees, it would immediately tell us. Because it doesn't just update a key and value here and make sure that they're the same. It will read 100 rows deterministically from one table, aggregate them up and write them to another table. But meanwhile, that table, it's going to read something and write it to a third table. Meanwhile, we've got a Kafka stream coming in that is all calling a different class of procedure that's interacting with this data in a different way. And basically, as much of Volt we can use in as much an intertwined way as possible, we've built into this app. And this is all open source. You can view it on GitHub/VoltDB/VoltDB. It's in the, I think, test apps folder. If we built this intertwined app, and then what we do is we run it. Sometimes we run it and leave it alone and just see if it runs safely for a while. Sometimes we run it and we fail the whole cluster and bring the whole cluster up from disk. Sometimes we run it and we fail individual nodes and rejoin those nodes. Sometimes we run it and we do whatever we can do. We fail a single link. We partition the network. We do whatever kind of evil things we can do. And we repeat that process just continuously in the background in our closet and in various public clouds. And so we've got some people here who've done really tremendous work automating that infrastructure, so that we basically can go into a room, bring up a dashboard, and see how many failures have happened in the last day and since we last checked the dashboard. What kinds of workloads were those failures? What builds and versions were those failures on? We can also look at performance. So we've got extensive performance tests and say, well, we made the latest version of VoltDB is significantly better in these areas, but for some reason it takes longer to restore when you rejoin a failed node for some reason. And that kind of insight took us years and years to build out. But it is really, really valuable in making sure that we continue to push the product forward, that we continue to trust the product we're shipping, and that we don't basically break customer workloads. Because for almost every little performance detail, there's some customer out there that really relies on that particular kind of performance. Whether that's maybe they've got a workload that does some kind of ad hoc workload. Maybe they've got a workload that has really, really high contention on a small number of keys. Maybe they've got really complex Java procedures that run processing in Java. And so there's a lot of different dimensions to Volt performance. We've got customers with pools of clients connecting to Volt that have 100,000 connections to Volt. We've got customers that are using Kafka and they have no clients. They're just feeding Kafka streams into Volt. So there's a big surface area to test, and it's definitely a huge part of what we do here is verifying that we can ship this thing and still sleep at night.
Fascinating. Okay, yeah, I think you definitely covered the depth of the question.
Okay.
It was definitely good enough. Okay, so to begin to close off, I want to zoom out and talk about how you see the database landscape as a whole evolving. We're far beyond the idea of one size fits all, and Mike Stonebraker, who helped start VoltDB, was thinking about this a while ago, but so we're moving towards a world where there are more and more databases with increasingly nuanced feature sets. How should systems architects approach this buffet of databases and figure out which databases to choose for their holistic set of data management requirements?
It's a good question. So I don't know. Let's see where to start. So one thing that's really important to know about your data is how operationally dependent are you going to be on this database? There are a lot of systems where I can say, because I used to work at Vertica, which is an sort of an analytic focused database before I came to VoltDB. And in the early days of Vertica, this has somewhat changed. Selling an analytics system is a little bit of an easier sell because you can always add it to whatever else you're doing. load your data into it as well as whatever else you're doing, and run queries against it. And if it happens to provide a lot more value than whatever else you're doing, maybe you turn off the old system. But it can be an add, because largely it's just you're teeing the data that's coming from whatever your operational system is, and you're putting it into two systems, and you can query them together. Maybe it's more resources, maybe it's more licensing costs, but in terms of affecting your infrastructure, it's a pure add-on. And so looking for systems that are pure add-ons is a lot easier, and in some ways sometimes more fun than looking at systems. Typically, VoltDB is sort of a different class of system where, for the most part, people are building applications that are built around VoltDB. They're building applications where, sometimes it's a legacy replacement. I say in telco, a lot of times people are ripping out times 10 because it doesn't virtualize well, because it doesn't work with their sort of network virtualization push, because it doesn't cluster well, because it's ungodly expensive. But many of these apps are sort of greenfield apps where people are building a new applications that weren't possible with sort of technology from 20 or 30 years ago, and they're building it around VoltDB, and they're building it very much where VoltDB is very hard to swap out. And this is a pro and a con, right? VoltDB is a very specialized system, so by using sort of stored logic, we can get performance characteristics that are very predictable, data safety that is really very good, much better than many of the other systems that use asynchronous replication. We have a lot of advantages, but it's a very much a, it's not like switching MySQL for Postgres. I'm building an application, and VoltDB is coming along for this ride. So that I say that there's two differences here. And if you're picking an application where if that application fails, if that database doesn't work out, you're going to basically have to go back to the drawing board or rewrite things. It's a more challenging sell for us. However, I will say it's a much more rewarding sell, and it's a very sticky sell for us. So once we get over that hump of people willing to say, like, I'm going to go all in with this company, it's much easier for us to sell to other use cases in those companies. It's much easier for us to say, hey, as your business grows, let's expand our relationship. And people are generally, I think the customer satisfaction for Volt is very high, and it's been really satisfying that way. So it's not quite a direct answer to your question, but it's important to make that distinction between the sort of the two kinds of databases that you're going to be adding to your system, and how choosing them is a little bit different. You can you have a little bit more on the analytics side or on the add-on side, the ability to sort of play around. And it's a little bit it's sort of different to play around on the operational side. Right.
No, I think that sounds like that's a great answer, a great way to conclude the conversation. John, thanks for coming on to Software Engineering Daily. This has been really interesting. I'm a fan of VoltDB, and I look forward to hearing what you guys do in the future.
All right. Thank you very much for having me, Jeff.